This is the first of two modules discussing CUDA programming basics. It assumes some familiarity with basic CUDA concepts, such as CUDA threads, thread blocks, and kernels, which were described in the previous module, CUDA Programming Model Overview. This module discusses the CUDA software stack and some aspects of compiling CUDA code, along with the basics of GPU memory management. Only the basics of CUDA programming are presented in these two modules. For additional features of the CUDA API, please consult the CUDA Programming Guide. CUDA installation consists of three components: a driver, a toolkit which contains everything needed to compile CUDA code, and an SDK consisting of code examples. Detailed installation instructions for different platforms are contained in the Quick Start guides located on the CUDA Zone website, along with the downloads and other CUDA resources. CUDA is a heterogeneous programming environment where both CPU and GPU are used by an application. The developer can write a single source file containing both CPU and GPU code, where the CPU code can leverage a variety of CUDA-optimized routines, such as those found in the BLAS and FFT libraries. The NVIDIA C compiler is a compiler driver that splits the GPU code from the CPU host code. The CPU code is compiled by the native host compiler, and the GPU code is compiled into PTX, or Parallel Thread Execution Object Code. This slide represents the compilation path of CUDA code. Any source file containing CUDA language must have the CU extension and be compiled with NVCC. NVCC is actually a compiler driver that invokes all the necessary tools and compilers for both CPU and GPU code. Although not the default case, one can specify via options to NVCC that CPU C code or device PTX object code be generated. PTX object code is an intermediate device-independent representation that is then compiled to the particular device. CUDA executables contain the PTX code in addition to target code, so that new target code can be generated on the fly when the executable is run on a device different from what it was compiled for. There are 4 different build configurations one can use when developing CUDA code. Using NVCC with no flags builds release mode. The -G flag can be used to build debug mode. The -device EMU flag builds device emulation mode, where all code runs on the CPU, but the executable contains no debugging symbols. The -G and the -device EMU flags can be combined to build debug device emulation mode, where all code runs on the CPU and all code contains debug symbols. Having briefly discussed the CUDA compilation process, we now turn our attention to writing CUDA code. The first topic we discuss is managing device memory. The CPU and GPU have separate memory spaces, and both these memory spaces are managed from the host or CPU. Device memory management from host code includes the allocation and deallocation of memory, as well as data copying between host and device. The device memory we discuss here is a global memory discussed in the Programming Model Overview. Device memory allocation, assignment, and release functions are similar to C's functions. Where C has malloc, memset, and free, CUDA has CUDA malloc, CUDA memset, and CUDA free. The prototypes between the C and CUDA functions are similar, except that CUDA malloc returns the pointer to the address of allocated memory on the device as the first argument. This is because all CUDA API functions return an error code that can be used to verify successful completion of the call. CUDA error reporting is discussed at the end of programming basics. The segment of host code on this slide demonstrates the use of these functions. This segment of code allocates, initializes, and then deallocates a 1024-element integer array. Note that the declaration of a device memory pointer is the same as a host memory pointer. In order to distinguish between pointers to device and host memory spaces, programmers often choose variable names with D and H prefixes or suffixes. To initialize the array from host code, CUDA memset can be used. As A sub D points to an address in the device memory, access to it must be performed through CUDA API functions on the host and not by assignments. Once memory is allocated on the device, data can be transferred to and from the device using CUDA memcopy. The first three arguments to CUDA memcopy follow the format of C's memcopy: the destination memory address, the source memory address, and the number of bytes to be transferred. The last argument is an enumeration that indicates the direction of the transfer in terms of the host and device, and can take values CUDA memcopy host to device, CUDA memcopy device to host, and CUDA memcopy device to device. This is needed because pointers to host and device memory are declared the same way. The source and destination pointer declarations provide no information on which memory space they point to. As far as synchronization between host and device is concerned, CUDA memcopy is a safe call. It blocks the CPU thread and returns after the copy is complete, and will only initiate the copy after all previous CUDA calls have completed. There are asynchronous memory transfer functions that can be used, and these will be discussed in the memory optimization modules. To demonstrate the use of CUDA data management, we step through a simple code that allocates memory for 4 arrays: 2 on the host, A sub H and B sub H, and 2 on device, A sub D and B sub D. The code initializes A sub H, transfers this data to A sub D, then performs a device-to-device transfer to B sub D, and then back to the host in B sub H. Remember that all of this is done in host code. There is no device code in this example. In the highlighted section of code, note that pointers to host and device memory are declared in the same manner. The H and D suffixes are simply a convention used to aid the programmer in distinguishing between the two memory spaces. The highlighted section of code in this slide calculates the number of bytes to be allocated for each array, and then uses C's malloc function to allocate the 2 arrays on the host. Likewise, CUDA malloc is used to allocate the 2 arrays on the device. Here, the host array A sub H is initialized, and the data is transferred from A sub H on the host to A sub D on the device using CUDA memcopy. Note that the enumeration CUDA memcopy host to device is used, and the order of the first 2 arguments is the destination followed by the source, A sub D and A sub H. CUDA memcopy can be used to transfer data between 2 arrays on the device, as is done here, from A sub D to B sub D. The final transfer is from B sub D on the device to B sub H on the host. Once again, notice the order of the first 2 arguments in relation to the last argument, CUDA memcopy device to host. The 2 host arrays are now compared element by element. And finally, host arrays are deallocated using free, and device arrays are deallocated using CUDA free. The previous example of GPU data management concludes Part 1 of CUDA Programming Basics. All of the CUDA API discussed to this point executes on the host. Part 2 of CUDA Programming Basics focuses on GPU code.